So, review for Part 2, Module 5, beginning Module 6 lecture. So, all of those things are names for numbers, right? A couple is 2, all right? You're out walking with your loved one. Woohoo! That's a couple. Oh, look at that sweet couple. All right, that's what you call them. It's a sweet couple. Well, if you were out walking with 6.02 times 10 to the 23rd of people, you'd be walking with a mole of people. That's the concept of a mole, all right? So it's a name for a number. A mole is also a pesky little critter that digs in your garden. But we're not talking about that mole. We're talking about the name for a number, and the number is 6.02 times 10 to the 23rd. October 23rd is Mole Day. Yes, sir?
How come if it's a name for a number, if there's a formula to it? You said a mole is 6.02 times 10 to the 23rd. Why don't they just multiply that out and have whatever number is produced called a mole?
Well, you could. It's just that's a lot of zeros to mess with. Yeah, that's all. You're right. You got to deal with scientific notation, and I don't like it either. But it just is. It's a lot easier to write than 23 zeros. Good question. Thank you. Thank you. But what you got to get is the fact that that is the number of something. All right. It's a mole is 6.02 times 10 to the 23rd of something. Incidentally, it's also Avogadro's number. Emilio Avogadro, all right? That's the guy that discovered the concept, and so that's his number. It's not Hulling's number, it's not Grant's number, it's Avogadro's number, all right? So that's another name for a mole, which is 6.02 times 10 to the 23rd. Are we all good? We got that? Pretty simple, but here's the next deal. So, with regards to that, look at your periodic table one more time. So, the atomic mass number, we just identified it. It's right under the atomic symbol. And for neon, it's 20.2. That's the atomic mass of neon, number 10, all right? As it turns out, this is the way it works. In grams, so the mass of one atom of neon is 20.2 AMUs, all right, atomic mass units. But if you go 20.2 grams of that stuff, as it turns out, that's 6.02 times 10 to the 23rd atoms of neon. All right? That's just the way it works. A mole of something in chemistry is 6.02 times 10 to the 23rd atoms of that stuff, and that number in grams is the same number as atomic mass units, as the atomic mass. All right? So, look at your periodic table. Number 17, chlorine. So, the atomic mass of chlorine is 35.5 AMUs. But 6.02 times 10 to the 23rd atoms of chlorine is 35.5 grams. How about that? So, look at silicon, number 14. 28.1 AMUs is the mass of one atom of silicon, all right? But 6.02 times 10 to the 23rd atoms of silicon is 28.1 grams, all right? Now you say, how does that work? And I say, I don't know. It just does. It's a beautiful thing. It's a beautiful thing. But you have got to grasp that concept. You have got to grasp that concept, particularly of the mole concept and the fact that the number that sits right underneath the chemical symbol is the number of grams for one mole of that particular element. All right? Now, who's got a question about that? Come on, I know you do. So do we get this? Now, what about H2O? All right? So there's 2 hydrogens in that stuff and 1 oxygen. So, looking at your periodic table, we see that there's 2 hydrogens, so I'm going to add 1.01 plus 1.01, usually that's 2.02, and then there's 1 hydrogen, that's 16, so if we do the hard math, we get 18.02, all right? What would be the mass of that stuff? All right, it would be 18.02 AMUs, all right? The mass of 2 hydrogens and an oxygen is 18.02 AMUs. Well, how many moles is that? Well, as it turns out, it's 18.02 grams of that stuff is a mole of H2O, all right? So that is then the concept in terms of the last statement, molecular mass. We added it up in AMUs. And then in terms of what it means to figure out the number of moles in a particular molecule or compound, you add up the number of grams of each of the elements in that compound, you add them together and you got it. All right, that's the number of grams for a mole of whatever it is that you're asking about. Okay? Look at page 2 of your notes on Module 5. An atom's mass in AMUs tells you how many grams it takes to have 1 mole of those atoms. That's what I've been saying. All right? A molecule's mass in AMUs tells you how many grams it takes to have 1 mole of those molecules. What's a molecule? It's just a bunch of atoms together, like carbon dioxide or water or methane or whatever it is. You add up the various elements in that molecule, and whatever it is in AMUs, you make that grams, and you got a mole of that stuff. All right? In chemical equations, this is the last thing that is vital for you to grasp at this point in time. So in chemical equations, the coefficient, just take a look at one here, and actually there's a picture I want to refer you to one more time too. So go to page 153 real fast in your textbook. It just makes it so much better. So look at the chemical equation there on page 153. Methane gas plus oxygen yields carbon dioxide and water. For the sake of reminding you that you have to know how to balance chemical equations too, let's just check it real fast. Let's see, I see 1 carbon on the reactant side, and yep, lo and behold, there's 1 on the product side. Let's see, 1, 2, 3, 4 hydrogens on the product side, the reactant side. 2 times 2 on the product side, that adds up. There is 2 times 2 oxygens on the reactant side. There's 2 in the carbon dioxide and 2 in the water. So voila, we got a balanced chemical equation. And the whole idea is that they gave you one there, but I just wanted to walk through the process one more time, all right? Because it's vital that you do that. So in chemical equations, I'm reading from your notes again, the coefficients which appear to the left of each substance tells you how many moles of that substance must be used in the chemical equation, all right? So remember, why are we even talking about moles? Why can't we deal with AMUs? Well, we introduced that a second ago. AMUs are so small, you can't even begin to deal with AMUs in a reasonable way. It's too small a number. You'd have to use too many AMUs to try to figure out anything, and you really can't measure it anyway. So the reason we deal with the mole concept is that's something we can handle. Turn back one more time. We're going to get to the final thing. Look at 147, page 147. So remember what I said. We added up the hydrogens in the water. It's actually 18.04, but we won't be technical. So there is a mole of water, all right? in terms of the picture there on the right. See the little, where the meniscus is at the bottom? Incidentally, the little doodad that's floating up above it, the plastic red, orange thing that's floating up above the orange thing on the bottom, that's supposed to be where you push that thing down and sit it right on your meniscus. That way you can get a right amount, or at least you know you've reached the right amount. But anyway, that's 1 mole of water there. See, that's something you can work with. It's enough water that you can handle that. You can recognize it, you can see it. Look at grams, 58.5 grams of sodium chloride. Once again, that's a pretty good amount of salt there. That's something you can work with. A mole of salt is something that's tangible enough for you to do work with it in terms of chemistry. Same thing with iron fillings. And though you can't see the helium in the balloon, the idea there is that helium filled up that much volume there in the balloon. It's an amount that you can work with, okay? So that's the reason we're gonna mess with moles. It's something in terms of working your recipe. Remember what we said when we introduced chemical reactions, that it's kind of like cooking and it's a recipe. Well, now we found out a way to really do the measurements in the recipe. And as it turns out, the big numbers to the left of the molecule is the number of moles. Remember, we've described it as the number of molecules, and that's correct. We say it that way too, but that's the number of moles, all right? We're gonna introduce another word in just a moment in Module 6. It's also called the stoichiometric coefficient, all right? You don't have to write that down because we're gonna look at it in Module 6. And I defined stoichiometry for you, but I don't want to do that again this time. We'll talk about it in a second. So, notice the methane, CH4 on the reactant side. I'm back to page 153. The methane on the reactant side, page CH4. There's no number out in front of that. Does that mean that there's no moles of that? No, that's not what that means. It just means there's 1 mole. You don't write 1. As we've said before, you don't write 1 when there is just 1, all right? If there's more than 1, you write that. And so that's what we did. There's 2 moles of oxygen. Notice oxygen, the what? The homonuclear diatomic. It always exists that way. 1 mole of CO2, because there's no number next to it. 2 moles of water on the product side. So that is a quick and dirty version of the last half of Module 5, and it's vital that you get it. So, did we get it? Not quite half of you Zoomed last week, and as I said, technical difficulties with the video, so you guys are on your own for it. And maybe you did fine with it. Maybe I've made it worse. But anyway, are we good? All right. Well, good. That's great. It's simple stuff relatively, but you know, you gotta get it because we're fixing to go deeper. So what I'm going to hand you now is the test and the notes for Module 6. Let's talk about the test before I give it to you. Just a lot of questions about the moles and stuff, all right? In the first part of the module, we talked about the types of chemical reactions. Combustion reactions in particular you need to be aware of, because there's a combustion reaction, but there's 3 forms of it, right? The complete combustion, where you produce carbon dioxide and water. The combustion reaction with less amount of oxygen, where you produce carbon monoxide and water. And then the form of combustion when you have extreme reduction of oxygen and you're producing carbon, soot, and water, that's the one to remember. Formation reactions, decomposition reactions, you'll be asked to identify them, and let's see, write balanced chemical equations, and then of course to identify mass and that sort of thing of various elements. So it's the stuff we just went over. Any questions about Module 5? Anything at all? Okay, let me give you this stuff. Fortunately, this time, just did one page, you got one page of Module 6 notes, and one page of test. Could be doing worse. This is not too bad. Okay, turn over to page 163. So what we're going to do this module is another thing that you will build on for the rest of the course. And I might add, conceivably this is the hardest part of the course, all right? It's not hard stuff, but it's tedious. It's steps, all right? It's taking the factor label method that you learned in Module 1 and applying it to chemical reactions, and applying the factor label method such that you cancel, in this instance, moles or grams. And it's not hard, but it's just tedious. That's the easiest way to describe it. So in terms of this, let's go to the back of the book and define stoichiometry for you. All right, it's right there on page 163, but let's do this. So, stoichiometry, if you'd write this down, please. The numbers that appear to the left in chemical formulas, in a chemical equation, That's the coefficients, excuse me. Start over. The process by which the amount of one substance in a chemical reaction is related to the amount of another substance in a chemical reaction. All right, one more time. The process by which the amount of one substance in a chemical reaction is related to the amount of another substance in the chemical reaction. All right, so we will spend a few minutes explaining that. Let me define limiting reactant for you as well. I'll use the glossary too. It's the reactant that runs out first in a chemical reaction, and it determines the amount of products made. So a limiting reactant is simply the amount that runs out first in a chemical equation. So right off the bat, you'd say, well, why would you want to do that? Why wouldn't you make it so that there's nothing left in the process of a chemical reaction? Well, that's a good thing, but sometimes it's even a better idea to have a lot of one thing in terms of what you might be trying to produce, and we'll explain that. So limiting reactant is the reactant that runs out first in a chemical reaction. It determines the amount of products made. All right, just a little tiny math reminder for you. Look at the bottom of page 163. So you remember a little bit in your algebra. You've got an equation y plus 3 equals x. That also worked in your geometry in terms of plotting lines and stuff like that. So if y is 2, then you fill in y for 2 and you do the math, and so you know x has got to be 5. And so that is something that is going to actually relate to, as we will see, in terms of chemical reactions. I've got notes for you, and I think we're just going to do that. The discussion of limiting chemical reactions is on page 167. Let me read from your notes first, though. When reactants are added so that all the reactants are used up, we say that the reactants reacted completely. Right? Pretty straightforward. I mean, the language there is specific, so that's why I've got it in quotes. The reactants reacted completely. All right? When a chemist adds a lot of extra reactant in order to make sure that the other reactant is the limiting reactant, we say that the chemist is adding excess reactant. All right? And in terms of that, there's an excellent example in terms of your we're going to look at it here in just a second on page 172. I think that will help you figure this out as much as anything. But I'm still reading from your notes. So if you're reacting something and you want to produce something in particular that requires perhaps it's a decomposition reaction of some form, but different in the sense that you're not decomposing down to constituent elements, though you may want to do that. But the point is, if you have something that you want to get something out of, and you're reacting it with something in order to do that, what you want is a lot of the thing that you're reacting it with, so that you get all of what you want out of what you've got. And again, the example on page 172 will probably explain that better than I just did. The numbers to the left of each substance in a chemical equation are so important, they're so important that they have a specific name. All right? We called them the number of molecules. We called them the number of moles. And now, as I told you a little bit ago, we're going to call them something else now. We're going to call them stoichiometric coefficients. they provide a way of converting from the number of moles of one substance in the equation to the number of moles of any other substance in the equation. So the point is this: given a chemical equation, if you have a certain number of moles of something in that chemical equation, you can figure out how many moles you might need of another reactant, or how many moles you will produce in that chemical reaction. You're able to compare the number of moles of one substance, of one compound, of one element to the others in a balanced chemical equation and determine how many moles you're either going to produce or how many moles you need in reactants in that chemical equation. You can relate just one item in your equation to all the other items. That's what stoichiometry is doing. And that's what the stoichiometric coefficients allow you to do. The stoichiometric coefficients are also relate the volumes of gases in a chemical equation, moles and liters. So it relates both moles and liters. In a moment, we're going to introduce that concept of gases. Remember, I told you before I didn't care about state. I didn't care about you acknowledging the different states in terms of what the reactants or the products were. Well, this will be the one exception. We're gonna be sure we identify what's a gas and what's not in a chemical reaction. But before we get there, let's just look at this example in terms of what I'm talking about, both in terms of relating something in a chemical equation and now specifically with regards to limiting reactants. Look at example 6.4 on page 172. Some ores contain a small amount of precious metals that are in compounds with many other elements. So you're digging and you find something that's a little shiny, but it's in a big rock of something, a bunch of other stuff. For example, one common ore found on Earth is KAAgC2N. Now, silver, which has the chemical symbol Ag, is a precious metal, increasingly precious, I might add, and is useful to be able to extract that Ag, that silver, from that complicated compound there, the KAgC2N2. All right? The following reaction accomplishes this. So they're kind to you. They've given you a balanced chemical equation in this thing. So if you've got two molecules, 2 moles, the stoichiometric coefficient of 2 of KAgC2N, and you put that plus energy of some form, but you put that together with zinc, all right, and react it, you're going to get 2 moles of silver, 1 mole of zinc C2N2 aqueous, and then 2 moles of KCN. And so, if a chemist adds 5.61 moles of KAgC2N2 to excess zinc, how much pure silver can be made? All right? So, the first thing I want you to see in this example, and then the next thing is the process of stoichiometry, and we're running out of time. We're going to go over this again next week, though, just because really next week is simple stuff, molecular and empirical formulas, so we don't have a lot to do next time. So if you're looking at this stuff and you've by chance looked at your homework and you're going, I don't know about this stuff, we're going to go over it again next week because we had to hustle. But so, in terms of the example of limiting reactants, what you want is a whole ton of that zinc, not literally, but you want a bunch of that zinc in the presence of that silver ore to completely react all of that silver ore. All right? So in reality, if you're reacting this in excess, you're going to end up with 2 moles of silver, a mole of zinc C2N2, 2 moles of KCN, and a whole bunch of zinc in addition, all right? Because all the zinc will not have reacted. But that's the concept of limiting reactant, and an excellent example of why you would do that, all right? Is there questions about limiting reactants at this point? You get that idea? Yes, sir.
Quick question, you said that you would end up with a bunch of excess zinc, right?
If you had a whole bunch of zinc, yes, sir. Yep. And that's the whole idea of reacting something like silver ore.
So theoretically, if they had put like
You'd add
5 zinc instead of 1, you would also have plus 4 zinc over on the side.
right, conceivably. And you would still get in terms of the chemical reaction and the balanced chemical equation, you would still just get 1 mole of that zinc C2N2 compound, but then you'd have a whole bunch of zinc, just, the element of zinc left over as well. Make sense? And based on this chemical equation, you would not get any other zinc compounds as well, just those. Good question though. Thank you. Thank you. You guys are probably better than any class I think I've ever had for questions. I really appreciate it too. But here's the deal. We're almost out of time. So what they want to know is how much silver can be made in terms of moles of that stuff if instead of 2 moles of KAgC2N2, you actually had 5.61 moles of it. All right, and that's what you do a lot of times. I mean, if you're digging ore and you just got a certain amount, you didn't necessarily measure to the specific amount to go in the chemical equation. You've just got an amount. All right, and in this instance, it's 5.61 moles. And how do we know it's 5.61 moles? Because we measured it, it's a number of grams, and we did a calculation to figure that out, which we're not there yet. We're actually going to do that next, and that's really going to blow your mind, but it shouldn't. It'll be all right, I promise. So, but look at the specifics of this chemical equation, and they walk you through really good in these examples. So, a reminder, your homework was due today, and your tests. I gotta have your tests. So before you go, just drop them off, all right? Your tests from module 4. So drop them off before you go. But let me finish lecturing, and then I'll let you go, and you can drop off your tests. So excess zinc is added to this stuff, and now they're explaining to you that look at what happens in this balanced chemical equation. 2 moles of that silver ore make 2 moles of silver, all right? How do you know that? Based on the balanced chemical equation. And because they tell you right there in your exam. But you've got 5, according to the question, 5.61 moles of that stuff. And so here it comes, there it is, it's the factor label method. Yay! So there it is, 5.61 moles over 1. We always set it up over 1. So in terms of that stuff, we have 5.61 moles, but the balanced chemical equation says we make 2 moles of silver from 2 moles of that silver compound. So in terms of our factor label method, we're going to set it up such that we cancel the silver ore and then do the math, because the correlation between these two is direct. So however much we've got in terms of anything in a balanced chemical equation, you can relate that to anything else in that balanced chemical equation. So in this instance, The the silver ores cancel. You do the math, you divide 2 into 2, so you immediately see what's going to happen. You're going to end up with 5.61 moles of silver if you started off with 5.61 moles of the silver ore. All right, that's just the first example, and we've got to quit. I promise you we're going to do more examples of this next week, because that is stoichiometry. It's comparing one of the ingredients in your recipe to any of the other ingredients, and you can figure them out. All right, thank you guys.